All right, I'm going to postpone the formal lab write-up 1 week. And so that'll be due 2 weeks from now. But you're going to have to do an extra step in the procedure. The extra step in the procedure is you're going to take about half the crystals that you formed last time and try to recrystallize them. The way you recrystallize it is you just dissolve the crystals in solution again and then precipitate it. Each successive time you recrystallize should become more and more pure, but this time we're going to try to grow some bigger crystals. And the way we're going to grow the bigger crystals is we don't want to rapidly precipitate everything out that we can. And so, for example, that means we aren't going to use an ice bath. The purpose of the ice bath was to bring down the solubility to precipitate out the crystals quickly, right? So we could filter them. But we aren't going to filter them today. We're going to filter them next time. And so we're just going to dissolve them in, well, how much water should you dissolve your crystals in if you want to try to recrystallize them? A little bit of water. Well, how much is a little bit of water? And so I get asked this question all the time, 20 milliliters, 10 milliliters. If you were to write a lab manual and say, okay, dissolve your crystals, well, you're probably going to pick some volume that works for everybody, like 50 milliliters. But that doesn't work for everybody. That's too much water for a lot of people and maybe not enough for some other people, depending on how many crystals they got, right? Well, they probably won't do not enough. They'll probably overshoot it, so it works for everybody. But for you, how much water should you use? A little bit meaning what? No, we don't know. What you do is you just keep adding until it all dissolves, and then you stop adding water. And so you want to use what we call the minimum amount of water to dissolve your crystals. That way they should crystallize out a lot easier. And that minimum is you just have to be careful. You just don't dump in a whole bunch of water, right? Otherwise you're going to have a hard time getting any crystals. And then you can add a little bit of ethanol. You don't want all your crystals to crash out the solution because of, did I talk about nucleation and growth? Yeah. We just want, hopefully we just want to seed or nucleate just one crystal or a few crystals and have those grow big over the weekend. All right, so that shouldn't take very long, and don't bother heating it. We're just going to do this at room temperature. There's no reason to heat it unless solubility is hugely different. So, and we aren't going to cool it. That would be getting to more extreme cases. All right, so any questions about that? Is that clear? The formal lab write-up will be due in 2 weeks then. And so that doesn't mean you should just wait until the last day to put everything together. I mean, this is just an extra paragraph on your report. It's basically a few sentences in the experimental, and a paragraph in the discussion. Okay. All right, let's take a look at the other ions that we're going to look at. So let's do aluminum next, since we took a look at the flow chart for aluminum. But we didn't write down all the observations and equations that we see for that. And so if we had aluminum in our unknown, we'd take our aqueous unknown, add HCl. Aluminum is going to give us no reaction. The equation for that would be Al3 plus H plus Cl minus. I'll do this in anionic form this time, but see, nothing's going to happen. And then we take the solution from 1 here, step 1, and then add ammonia. And here we expect for aluminum, we expect a precipitate, kind of a low density, white, colorless precipitate. And so the reaction for this is aqueous ammonia is a precipitating agent for hydroxide. So 3 ammonias, 3 waters gives us aluminum hydroxide, solid, 3 ammoniums. So the driving force of this metathesis reaction is precipitation of aluminum hydroxide. Okay, 3 is, what do we do here? Do we add? Well, to the precipitate in 2, we add excess sodium hydroxide. We didn't want to add sodium hydroxide earlier because you get a lot more precipitates, but now it's okay because sodium hydroxide should only react with the, so the white precipitate dissolves, we end up with a CCS. Technically that's, I mean, we might have other colors in there because of other species, but if it were just aluminum, that's what we expect to see. And that's because aluminum reacts with hydroxide, aluminum hydroxide, which is a solid, reacts with another hydroxide to form this. Tetrahydroxyaluminate. So I talked about why iron, why not iron? Why not chromium? Why don't those form the tetrahydroxide complexes as well? Did we talk about that? Yeah. All right, and then from here, we add some hydrogen peroxide. So solution 3 gets some hydrogen peroxide, which gave us no reaction. I mean, aluminum only has 3 valence electrons, and once it loses all 3 valence electrons, it doesn't lose any more. So aluminum plus 4, aluminum plus 5. Things we wouldn't really worry about. Then what did we do? Well, we took the solution from 4 and then add some HCl to it. When we add the HCl, nothing happens, no change. It looks like no visible change. So maybe I should say visible. But in reality, even though it looks like no reaction occurred, there was a reaction that occurred. Right? When you add the HCl, you're going to attack the hydroxyligands. That's this. So look at my tetrahydroxyaluminate 3, and add 4 H pluses to that. And I'll get aluminum 3 plus 4 H2O liquids. And so it frees up the aluminum 3 from the complex. And actually, aluminum 3 though is still surrounded by ligands, but in this case it would be water ligands. And forms a hexaaqua complex. 6. Then we take the solution from 5, and then we add some ammonia to that. But this time we're going to add ammonia in the presence of aluminon. Aluminon is a dye. And so we just add it as a dyeing agent. Say you want to dye your shirt, you don't need to put a whole bunch of aluminon, just a tiny bit of aluminon in there. And we get a red precipitate. This red precipitate is very low density. The red precipitate almost looks like jello. It almost looks like a liquid. And so what you do is you centrifuge it. When you centrifuge it, you get something called the red lake. The red lake, because you get a gelatinous layer like this that's red, and on top of that you have water. And so it looks like the water's like the sky, and the precipitate's like a lake. So this is a red lake precipitate. It's a solid, it's not actually a liquid like a lake. And so the reaction for this is aluminum 3 plus 3 ammonias plus 3 waters yields aluminum hydroxide. But aluminum hydroxide is not red. Aluminum hydroxide is white to colorless. And so how do we get the red color? The red color comes from aluminon. Aluminon will complex with some of the aluminums in the crystal lattice, not all of them, just some of them as an impurity, and discolor our precipitate. And so I'm going to show this by writing a double dagger next to the aluminums, saying that there is some aluminon incorporated into the precipitate here, in the lattice itself, giving it the color. And so this is our red lake precipitate. Okay, that's for aluminum. So if we get the red lake, that's a positive test for Al3 plus in our unknown. Okay, then we move on to chromium. For the chromium test, we start off, with our unknown. If our unknown contains chromium, and we add HCl to that, then there's no reaction. That's chromium 3 plus H plus Cl minus. Nothing's going to happen. 2, we take solution 1, and then we add the ammonia to this. And we get a precipitate. This precipitate is supposed to be gray-green, but you'll get a mix of colors there. And so this is just chromium 3 plus 3 ammonias plus 3 waters yields chromium 3 hydroxide. So precipitate is 3 ammoniums. Okay, so we have another metathesis reaction, precipitation. And then step 3. To solution from 2, we add sodium hydroxide. Does anything happen? We're going to form the tetrahydroxo chromate 3 complex? No. So we get no reaction. And so the reaction here is that chromium is not going to complex. So chromium 3 hydroxide solid plus the extra hydroxide plus the extra sodium, nothing happens. Unlike aluminum. But chromium's like iron, not going to react. 4, we're going to take our precipitate from 3, and then we're going to add hydrogen peroxide. Then what happened? Well, what's going to happen is you can follow along on the flow chart. The precipitate dissolves and we get a yellow solution. So what is this yellow solution? The yellow solution is chromate. That's correct. And so let's take a look at the reaction chemistry. What kind of reaction is this? Is this a metathesis reaction? No, yeah, it's a redox reaction. And so the precipitate is chromium hydroxide solid. And then this is going to go to chromate, which is yellow in solution. And then hydrogen peroxide is the other reactant. Hydrogen peroxide goes to, we don't know. Yeah, actually we do know. We could just copy it off the chart, but. And so this is an example of a skeleton redox. In a skeleton redox, we know the major product, or products here. Chromate's a major product. We don't have chromium 3 hydroxide goes to chromate on our chart, so we got to balance this out. So 1 chromium, 1 chromium. The chromiums are balanced. Then we got 3 oxygens here, 4 oxygens here. So we balance by adding a water. And that gives us 5 hydrogens here, no hydrogens here. We'll balance that by adding H+. And then we look at the charge. -2 plus 5 is +3. That's got to equal 0, so +3 minus 3 will do it. And so we need 3 electrons over here. And so the balanced half reaction is like this: chromium 3 hydroxide solid plus H2O liquid. This is going to produce chromate plus 5H plus 3 electrons. So that's one of the balanced half reactions. The other balanced half reaction here, you can copy it off the chart, or you can just go ahead and do it. This one, after you do a bunch of these, this one you probably can do in your head if you want. But we have 2 oxygens here, no oxygen, so we'll need 2 waters. Gives us 4 hydrogens, we'll need 2 H pluses. And then the charge, we'll need 2 electrons. And so the other balanced half reaction, we'll write over here, it's going to be hydrogen peroxide plus 2H plus 2 electrons yields 2 waters. So let's add these up. Taking a look at the 2 balanced half reactions, I've got to multiply this one by 2. That gives me 6 electrons produced. And then I'll multiply this one by 3. That gives me 6 electrons consumed. So 6 electrons produced, 6 electrons consumed, electrons balance. All right, combining the equations, I'm going to do 2 chromium 3 hydroxide solids. Then I have 2 waters here, but I also have 6 waters over here. So you know what, I'm just going to cancel out these 2. Give me 4 waters left over here. Then I have 3 hydrogen peroxides. And I have 6 H plus here, but I got 10 H plus over here, so let's cancel those out. And then this is going to yield 2 chromates. Plus, what did I do with the hydrogen? So I'm going to have 4 H plus left over. It's 4 H plus. And then what did I do with the waters? It's 6 and 10, so this is going to give me, actually 6 and 2. This is going to give me 4 waters left over. All right, so this should be my balanced redox reaction. So let's just double check to make sure it's balanced. 2 chromiums, and then 2 times 3 is 6 oxygens, plus 6 oxygens is 12 oxygens. 2 times 4 is 8, plus 4 is 12 oxygens. 6 hydrogens here, 6 hydrogens there, gives me a total of 12 hydrogens. There's 4 hydrogens plus 8 hydrogens is 12 hydrogens. I have no charge on the left. I have -4 plus 4, which is 0. So no net charge on the right. And so this would be the balanced redox reaction. If we want, we could, we know that this reaction occurs, so we could take a look at the driving force here. Chromium 3 hydroxide, is that the oxidizing agent or reducing agent? Chromium 3 hydroxide is actually the reducer. When you look at the half reaction, it produces electrons. It's the reducer. The hydrogen peroxide is a oxidizer. How about going backwards? Yeah. Chromate is the oxidizer going backward. And what's the reducer? H plus and water. H plus and water. This is our reducer. Even though we have both of these together, it's really the what? Is it really the H plus that's the reducer, or is it really the water that's the reducer? It's really the water that's the reducer. Because the oxygen is going from -2 to -1. So going backwards, it's got to be losing electrons. All right, there's one problem with this though. We have H plus and we have OH minus. Did we get rid of this base that we added? No, we added excess base. And so we have hydroxide present. In other words, This reaction is not occurring under acidic conditions. This reaction is occurring under basic conditions. And so if we have plenty of hydroxide present from step 3 that we didn't get rid of, then the hydroxide is immediately going to attack the hydrogen ion to form water. And so for basic solution, we have to add an extra step to this. I have 4 hydrogen ions. I need to neutralize those with 4 hydroxides. And if I add that to the right, I better add it to the left, otherwise I screw up my balance. You know, I want to maintain the balance. And so let's go ahead and get the redox reaction in basic solution. So we've got 2 chromium, 3 hydroxides, plus 3 hydrogen peroxides, plus 4 hydroxides. Produces 2 chromates, plus, this is 4 hydrogen ions plus 4 hydroxides is going to give me 4 waters, but I already have 4 waters, so I'm going to combine all the waters and get 8 waters. 8 H2O liquids. And so this, in this case, the H plus completely dropped out of there. And we're left with this. We've got to make sure it's still balanced, you know, 2 chromiums, 2 chromiums, 12 oxygens plus 4, 16 oxygens. So it's 8 plus 8 is 16 oxygens. And then the hydrogens, we got 12 hydrogens plus 4, 16 hydrogens. We got 16 hydrogens. So that's balanced. Then we look at the charge, -4 here, -4 here, balanced. And so this would be the balanced redox reaction in base. Okay, what's next? What's next is, let's see, 4, go to 5. What's next is we heat it. You know what the heating step is for? To destroy the excess, not hydroxide. Yeah, we heat this, and so we'll take the solution from 4 and then heat it. We should probably see bubbles. Yeah. From CCG, clear colorless gas form. The purpose of this is to destroy any leftover hydrogen peroxide that was unreacted. And the hydrogen peroxide normally just decomposes, but it's slow. And so to speed up that decomposition, we heat it. And this is going to form H2O liquid plus 1/2 O2 gas. This is a redox decomposition. And so the heat, well, after the hydrogen peroxides reacted with the, you know, we're adding excess hydrogen peroxide. So we want to make sure we destroy any excess hydrogen peroxide that remains unreacted. Why? Why do we have to destroy the hydrogen peroxide? No, chromate is the limiting reagent, so the chromate's all done. We want the hydrogen peroxide to be the excess reagent over here. Hydrogen peroxide should be the excess reagent. Chromium 3 hydroxide should be the limiting reagent. And so we're going to completely convert all that chromium 3 to chromium 6 and chromate. And so we want excess hydrogen peroxide. Normally, have you been getting rid of any excess reagent? For example, we had excess hydroxide, and you go, I better destroy that excess hydroxide. Right? How do you destroy excess hydroxide? Just add acid. Did we do it? The hydrogen peroxide will not, because the driving force is this way. That means when we compare the strength, this is the oxidizer, this is the oxidizer. When we compare the 2 oxidizers, this one's stronger, this one's weaker. It's not going to react with the chromate. Hydrogen peroxide, what comes to mind? When you think about hydrogen peroxide, what chemical property immediately comes to mind? It oxidizes and reduces itself. Yeah, like that weird reaction I gave you on homework. Yeah, but normally what would you think of hydrogen peroxide? Based on the chart. It's a powerful oxidizer. It's like number 3, isn't it? Number 3 on the chart, one of those charts. 3, 4, whatever. And so when I think of hydrogen peroxide, I think powerful oxidizer. Well, powerful oxidizers are potentially dangerous, but powerful bases can be too. But we want to destroy the hydrogen peroxide. What's the purpose of destroying that? Because we didn't destroy the excess base, did we? No, we didn't. We just let it go. And so the hydrogen peroxide we're destroying now because we don't want it to react with something. And so the reason why we're destroying it now is because we don't want it to react with what? Well, hydrogen peroxide is an oxidizer, so look for a reducer that you don't want it to be oxidized. So is there any reducer in there? Chloride. Chloride's a reducer, but it's a pretty bad one. But it's possible. I mean, if you oxidize chloride ion, you'll form chlorine gas. That's not the main reason for this. There's a much more powerful reducer. What is it? Down the road. Down the road, we don't want our hydrogen peroxide to destroy this, because it will. Well, do we have to destroy it in this step? No, I don't want to destroy it here. Let's destroy it later. Or should we destroy it now? Should we destroy it now or destroy it later? What's the next step involved? HCl? So we have the HCl. So after we heat, then you add what? Ammonia. Well, tell me about what comes to mind when you think of ammonia? One thing that comes to mind is we're going to add ammonia and ammonium, right? If we add ammonia, that's a base. Ammonium is a acid. But we aren't worried about acid-base reactions because hydrogen peroxide is a oxidizer. And so we're worried about a redox reaction. So tell me the redox properties of ammonia and ammonium. Normally when I think about redox properties, I think in terms of electron-rich and electron-poor species. And so let me ask you this. This is a question I ask almost every semester in Chem 1A on a test. Ammonium, is that electron-rich or is electron-poor? A lot of people will say it's electron-poor because it's missing an electron. It's got a positive charge. Is it electron-rich or electron-poor? Electron-rich, Utama? Electron-rich is correct. Why is ammonium electron-rich? It's because of what? The charge on the nitrogen? The charge on the nitrogen is 0, isn't it? Or plus. The charge on the nitrogen is plus. Charge on nitrogen is plus. Is electron rich or electron poor? It's electron rich. You're still saying it's electron rich even though it has a positive charge? Is electron poor?
It's only one. Is it though? It's not rich. It's taking most of the electrons from the nitrogen.
When you say charge, we have different ways of counting charge, right? So you should have corrected me. You should have said, not that charge, the other charge. What's the other charge? This is the formal charge. What's the other charge? Oxidation state. That charge. And so when we look at the oxidation states, which is important for redox chemistry, this is -3. That's electron rich. And so this is a good field. And so we don't want any hydrogen peroxide because the hydrogen peroxide will eat up the ammonium ions, right? And what happens when you burn ammonium? Well, you get, hopefully you only get NOx, nitrogen oxides, which are toxic. So you don't want to breed those. But hopefully you aren't going to form even more hazardous species, like phosgene or something like that, which are used as like chemical warfare agents. But you don't know, because redox, I mean, there are people who burn methane and generate a whole bunch of carbon monoxide gas and end up dying from their heater or their cook equipment because it's spewing out a lot of carbon monoxide. And so when we have like potential redox reactions like that, it really depends on the conditions, what types of products we form. And so we could form a lot of different toxic agents here, gases. And so something like this should be done in the hood, but if you destroy your hydrogen peroxide before this, maybe you're okay doing it on the bench. If you didn't, then you gotta watch out because you're gonna get some redox reactions. Now tell me about ammonia. When you look at ammonia, what are the redox properties that you see in ammonia? Is it quite a bit different than ammonium? Yeah, it's still -3. And so ammonia and ammonium, redox-wise, they're the same. They're both electron rich. Both will burn with an oxidizer and form probably toxic gases. And so we gotta be careful. Even though in terms of acid-base behavior, they're total opposites. This one's a base, that's an acid. But in terms of redox, these are exactly the same. No different, pretty much. So we need to destroy the hydrogen peroxide so it doesn't destroy our ammonia and ammonium. The next step is to do what? Well, we're adding the ammonia to ammonium to solution 5 until it's basic, okay. And then we get a, what? Do you get a precipitate? No, we shouldn't get a precipitate. We're going to get a orange solution. How does the orange solution form? It has to do with chromate and dichromate. Chromate and dichromate have exactly the same oxidation state. They're both chromium +6. The only difference is one is stable in acid, the other is stable in base. Did I talk about the pH dependence of chromate, dichromate? Well, anyway, let's do this. So if I take 2 chromates, it's 2H plus, this will give me a dichromate plus a water. This is reversible. It depends. If the solution is quite basic, then the H plus concentration is very small, it shifts to the left. If the solution is very acidic, then the H plus concentration is high, which shifts this to the right. And so the way this works is that what we're going to do is, what are we doing here? Oh, this is already basic. This is already basic. So are you sure I add the ammonia, or do I add something else before that? I add HCl. I'm going to add HCl. This is the wrong step for that. Oh, I'm getting no change here. There's no reason. It's already basic, so why am I adding a base? And so here, what I'm going to do is I'm going to take solution 5 and then add HCl. And what should I get? I'm going to get orange solution. And so this should work now. And so this means I didn't have to destroy the hydrogen peroxide. I'm not adding ammonia just yet. But I'm going to take my 2 chromates plus 2H plus and then convert that to dichromate and water. This looks like a redox, but it isn't. This is just an acid-base reaction, Lewis acid-base reaction. All right, in the next step, what do I do? Okay, now I add the ammonia. So I'm going to take solution 6 plus ammonia, and this is going to give me a yellow solution. Probably the reaction I'm going to show by Le Chatelier's. And so if we look at this equilibrium in the previous step, 2 chromates plus 2H plus yields a dichromate plus a water. And then I add ammonia to this. The ammonia is going to attack the hydrogen ion, or the acid. And so this is going to form 2 ammoniums. So the more ammonia that I add, the more the H plus concentration goes down, and it shifts the equilibrium back to the left. And so I'll convert my dichromate back into chromate and acid-base reaction. All right, in step 8, what are we adding here? Barium chloride? Okay, solution 7 plus barium chloride gives what? A faint yellow precipitate. And so solution 7, this is just a metathesis reaction. Barium ions, like chromate ions, form barium chromate solid. So this would be the positive test for barium ions in our original, not barium ions. This would be the positive test for chromate ions, not chromate ions. This would be the positive test for chromium 3 plus in our original unknown. Okay. All right, I'm going to stop here and then let you guys get started with the reactions.